Hello everyone, my name is Preeti Chandrasekaran and this is my project on machine learning for predictive analytics, which I completed as part of my data science and business intelligence internship at AINE AI. Here you can see a few details about the project and the objectives of the project. We start off by importing the necessary libraries, then we load the dataset. We have about 51,000 rows and 58 columns in our dataset. And here we can see the names of the different columns in our dataset. This data dictionary describes what each column means. Then we have the first 5 rows, and we also observe the last 5 rows in our dataset using the head and tail functions. Using the info function, we can observe the data types of each column. We can see that most of the columns have numeric values of either float or integer type. We have around 36,000 customers who did not churn and about 14,000 who did. This translates to 71% who did not churn and about 28% who did. Here we can see how many NA values are in each column. Many columns do not have any NA values. In this question, we found out that 6 customers had 0 monthly revenue. We update the data frame to exclude those customers, and we also exclude the customers with 0 monthly minutes. Next, we calculate the percentage of missing values in each column. This is done by calculating the number of missing values, dividing it by the total number of rows, and multiplying it by 100. As you can see, the highest percentage of missing values is around 1.7%. So to answer this question, since all of the columns have less than 5% missing values, we can drop the rows with missing values. So we do this using the drop_NA function. Here we visualize the data with a box plot. We can clearly see the outliers for the two columns, and we remove the top 1% of outliers from these columns with the help of the quantile function. After removing the outliers, we plot the box plot again, and you can see that the outliers have been removed. We create a scatter plot of monthly revenue versus overage minutes, and we can see that there is a positive relationship between the two. When we further plot this relationship by taking churned customers and non-churned customers separately, we can see that this positive relationship is still there. Thus, we can infer that as the overage minutes increases, the revenue also increases. We use a category plot to answer this next question. We can see that when the active subscribers is 1, the monthly revenue tends to be the highest, and as the number of active subscribers increases, the monthly revenue tends to decrease. Here we create a crosstab of churn and credit rating. We can see that for all possible credit scores, there are customers who are churning. We can infer that the proportion of churned customers is greater for higher credit scores. Now we move on to some additional EDA. We find that a majority of the customers have a professional occupation. We also find that there are a greater number of married customers. We also find that from plotting monthly revenue versus monthly minutes, that there's a positive relationship between the two. Using a category plot, we found that the monthly revenue is fairly evenly spread out among the different income groups. Now that we have understood the different columns and their meanings, we define a function to create additional features. For example, percentage overage minutes can be derived by dividing overage minutes by monthly minutes. Percentage dropped calls can be derived by dividing dropped calls by monthly minutes. Similarly, we create the remaining additional features. Here we actually invoke this function to create the extra features. Then we define a function to separate the columns depending on whether they hold categorical or continuous values. Then we define another function which uses the chi-square test to help us determine which factors are important in terms of modeling. We currently have around 48,000 rows and 69 columns. We have around 34,000 customers who did not churn and the data of 13,000 customers who did churn. Thus, our data is imbalanced. In this code, we use oversampling to tackle this problem. Since we have a lower number of customers where churn is yes, we will simply repeat these data points until there are 34,730 rows for churned customers as well. After doing this, we can see that the data is now balanced. Then we filter out the data frame to include the important categorical columns by invoking the function that we defined, and we also keep all of the continuous columns. Since each column has its own scale, we use standard scaler for standardization. We use getDummies function to convert the categorical data to numerical data. Then we split the data into training and testing. We keep 30% of the data as testing data and the remaining as training data. We also drop the customer ID as it's not required for implementing the model, or training the model. Then we import all of the modules that we need, and we train the logistic regression model using the fit function and pass our training data as arguments. We store the probabilities of the predictions during training, and similarly, we also store the probabilities of the predictions during testing. We calculate the probability cutoff in this function by trying different thresholds, and we see which one gives the best F1 score. It uses a loop to try out all of the threshold values from 0 to 1 and calculates the F1 score for each one. Then we plot it for training and testing. So here we can see the F1 score for train at 0.4, we are getting the highest, and after that it decreases. So here we use the threshold 0.4 instead of the default value of 0.5. Then we use various metrics functions such as classification report and ROC-AOC score to evaluate the model. We use the confusion matrix function to obtain the number of true positives, true negatives, false positives, and false negatives. And this model has many false positives, which can explain why the accuracy is lower. We also built a random forest classifier. We specify the number of estimators as 350, which means that there are 350 decision trees being used. Like we did with the logistic regression model, we use fit to train the classifier with our training data. We also store the probabilities of predictions during training and testing. We use our efficient cutoff function. And from the plot, we can see that the threshold is around 0.53, whereas for logistic regression, it was around 0.4. We use this threshold to classify the customers as churners and non-churners. And using the same evaluation metrics, we evaluate the random forest classifier. Straight away, we can see improved precision, recall, and F1 scores. On observing the confusion matrix, we can see that there are much less false positives with the random forest classifier. Here we only have around 2,600, but with logistic regression, we had around 8,000 false positives. So we can conclude that the random forest model performed better with an overall accuracy of around 74%, while the logistic regression model only performed with an accuracy around 60%. And we used the random forest model to identify and visualize the top 20 important predictor features. The most important predictor feature was the current equipment days, followed by months in service and percentage change minutes. It's also interesting to see that many of our additional features which we created were in the top 20 most important features. That concludes this project walkthrough. Thank you.